the formula for the area of a triangle is something that you've seen in geometry courses all over the place. The 1/2 base times the height formula is very useful as long as you have the information that the formula demands. In particular, for it to work, you need to know the parameter h. The way we've been doing triangles has been to draw a triangle and to label known information as A, B, and C, and unknown information as gamma and alpha and beta, or known, unknown information relevant to the triangle, the three angles and the three sides. But if that's what you have and you want the area of the triangle, this extra bit is h, and that might not be something that's given when the triangle is described. So if you happen to know h, that's a perfectly good formula to use. If you don't know h, then you can recover h from other information. For example, if you label things so that you've got base B and side A and an angle gamma as things that you do know, then you could say what h is in terms of facts about the triangle. In particular, you know that the sine of gamma is opposite over hypotenuse. That would be h over a. And so h has, in terms of those other of the known things, it is a times the sine of gamma. And that means that if you use that in the formula 1/2 base times the height, you can express what the area is in terms of things that you're more likely to be given. In particular, lengths of sides A and B and the angle between them. You could do this trick for any combination of two sides and the angle between them. So you've got a family of formulas for the area of a triangle based on this little bit of geometry applied to the information on the sides of the triangle. So the area is 1/2 the product of the lengths of two sides times the sine of the angle between them. So let's say that three different ways. If the sides are A and B, then the angle between them is gamma. So 1/2 AB sine gamma, that's the formula we just derived. If you relabel the triangle so that the sides that you're given are A and C, between A and C lies angle beta. Between A and C lies angle beta. So 1/2 the product of the lengths of the two sides, the sine of the angle between them, and one more variation, the product of the lengths of sides B and C, and the angle between B and C is alpha. So any of those are reasonable. This is kind of like, you might remember when we talked about the law of cosines, how there is a matter of labeling, and the formula you choose to use comes from the symmetry of the labeling that you decide. So here's an example. Find the area of the triangle for which A equals 5, C equals 7, and beta equals 70 degrees. So think about what you know. A and C are the two sides, and the angle between is beta, that's 70. So we need 1/2 AC sine beta. 1/2 times 5 times 7 times sine 70. See if I can place this so that we can see what's going on. So it's 1/2 times 5 times 7 times, and now it's in degrees. Check to make sure it's in degrees, and we want the sine of 70 degrees. So I'll enter 70, the sine, and that was the product, so that was the last term. So overall 16.4 something. There, and that's the area that we can calculate for that information that's given. Maybe another example based on another formula. This one is a formula for the area of a triangle where you don't know any of the angles, and what you know instead is the lengths of the three sides. Geometrically, it ought to be the case that the three sides determine the triangle, and if they do, then there should be a unique area determined, and it's given by this formula originally derived by Heron. So here's what it says. The sides of the triangle A, B, and C, as given, are calculated so that you add up so that the A plus B plus C is the perimeter of the triangle, and divide by 2, and that's this parameter S in Heron's formula, and the area is S times S minus A times S minus B times S minus C. There is a consistency about this formula that you ought to notice, and you can borrow a trick from the physicists who do something to keep track of units of measurement and make sure that the algebra of the units of measurement makes sense. S, in particular, is the sum of three lengths of sides. So S is a measure of length, and if you subtract A or B or C, you're subtracting a length from a length. So the right units for S and S minus A and S minus B and S minus C are all length units. So we've got 4 length units, say inches or centimeters, say inches. So that would be inches to the 4th power, and you're taking the square root of inches to the 4th power to get square inches out. So at least there's that consistency that Heron's formula produces units that are consistent for measuring area. So this is the tool to use, Heron's formula for the area of a triangle. And let's try to make it work. 5, 8, and 11 for the triangle. So we'll label those sides that way. A equals 5, B equals 8, C equals 11. Let's get out what S is. 1/2 the sum of those three. 5 plus 8 plus 11 is 24. Divided by 2 is 12. And then the area is built from S as 12 for S. S minus A is 5, S minus B is 8, S minus C is 11. So what's under the radical is 12 times 7 times 4 times 1. 336, and you could leave it that way, or you could simplify it by factoring out a greatest perfect square under there. 16 times 21 is 336. So this is the square root of 16 times the square root of 21, and this is probably a preferable form. So two tools to find areas of triangles. If the information that's presented to you doesn't make either of those tools immediately useful, we've just been through law of sines, law of cosines, so that you can take information as presented and convert it so that you can use what you need for either Heron's formula or the area formulas that we derived earlier in the show.